So what that said is something you all know, which is that A/B testing is amazing. It works incredibly well, but it's weirder than I think we often give it credit for. In fact, it's weird. It's not an argument against it. In fact, it's an argument in this case for it. And you do these, throw out 100,000 trials and you get a 2% increase in your click-through rate. That's amazing. What's really weird about it is that we have no idea in almost all cases why one ad works better than another. You put the model over here, you put the model over there, and it turns out over here works better for that ad, but only for that ad and only at that time. We can't generalize and say, oh, yeah, you want to get a 2% boost, put the model on the left. No, that might work. That's why you're doing the testing. Sometimes it works, sometimes it doesn't. You can't predict. It may be based upon factors that we don't even, we can't even begin to list. We just don't know. All right, always put the model on the left, except having a clicker delay. Maybe it will turn out that only works if it's an ad for clothing, it's aimed at millennials, if the weather is foggy, if, who knows what. And that's the point. We don't know what. That's why we're doing the test. So it's just really weird that we have a technique that works so well, but we have no idea why it works in any one case. So this clicker thing is going to be a problem. I keep clicking and it takes maybe 5 seconds. I think maybe we should move to I hate to do this because there's lots of clicks, but can we do a manual thing where I will go like that and somebody will click?
Yeah.
Okay, so.
Get it again?
Work that time? Okay, we'll give it another try. So it may be that not only are there no such rules that you can derive from your A/B testing, it may be that it's different for each person. That model on the left works for the person on the right, let's say, for some reason because she had oatmeal that morning, and it just may vary from person to person. So this is a very, very weird situation to be in. A/B testing works. You should do it. You know, it's not arguing against it, but we should recognize it is weird that it works. And what's, I think, more important is that I'm sorry, let's go to manual. I hate to do it. But, it works because, in fact, the way the future works is weird, way weirder than we have thought. So we have thought for a long time, for about 300 years, that the future works like a clockwork. The way the universe works is pretty much like a clockwork, where there are pieces that interact, and one touches another and turns it, and we can figure it out. And if you want to affect what happens in the future, well, you can affect the mechanism. You adjust one of the levers, you turn one of the dials, one way or another, and we can, in a predictable way, have an effect on what's going to happen. So you can trace this back easily to Isaac Newton. Newton did not actually hold with the clockwork metaphor because there was no room for God in the clockwork, but he gave us what we needed in order for the clockwork metaphor to make sense. So over his objections, we came to this idea, this way of thinking about the universe, which says that I don't feel conspicuous doing that at all. That's fine. That the universe follows some basic, simple rules. Oh, you want to predict where the planet will be or when the next eclipse will be, you can. We have now those rules. And those rules, those laws, apply equally well whether you're predicting the eclipses for next year or the eclipses for 1,000 years from now. All you have to do is change the numbers. There's no more work. Just plug in different numbers and you get your answers. It's pretty awesome, actually. So we got the clockwork metaphor because in the Newtonian world he gave us a small set of simple laws that apply everywhere, the same everywhere, which is actually, we take for granted, but was a huge conceptual shift in our thinking. And by coincidence or by divine intent, these rules happen to be ones that are knowable by humans. They're not beyond, we can know them, and now we do. And so that's how we thought the world works, and you can see how the clockwork sort of captures that. Very simple set of rules governing it. And so what we've done in the Newtonian world is we build models, and the model, as I'm sure you know, is takes a set of objects and specifies how they interact in a predictable and regular way. that these things affect. So we do this for the orbit of the moon, where it's a mathematical thing thanks to Newton. We do this for organizations, where we map out the flow of power or responsibility or workflow or something. We do this economically for our business with spreadsheets that can be incredibly complex, or that we can play with, we can alter, put in a different number and see what happens. But the spreadsheet reflects the factors that we think explain our business, if we've done the spreadsheet well. Even in 1949, this guy invented a physical model of the British economy using pipes and stuff he got from a hardware store and he salvaged from a plumber. And it's water pipes and pumps and reservoirs. This represents, you can turn up the pressure on taxes physically, turn the spigot and see what effect that will have on individual savings. And it worked. It was a very simple model, but it worked, thanks to water pressure and valves and faucets and things. So we have a bunch of different ways of modeling our world in different domains. In every case, we think, anyway, that these models reflect the way the world works, that these are accurate representations of how the world works. Sorry, I went too far. That was my fault. I double-clicked, and I apologize. Thank you. I didn't even. So now we have a new type of computing, though, which is called machine learning. And in one type of machine learning, and those of you who are data scientists will know just how wrong and superficial I'm being, in a way that I am not a data scientist, so I don't know. Nevertheless, in one of the types of machine learning, something called deep learning, we actually have what is at least close to an idea of the future that does not rely upon models, at least that we can construct. So this is not what I'm talking about. This is the before, not the after. So before, a computer, Deep Blue, beat the chess champion Garry Kasparov in the traditional computer way, which is you give the computer the set of rules for chess, and you give it then a few other variables and things to consider, such as how much a piece is worth and making sure the king is safe and so forth. And so you draw a model of chess. This is how you play chess. And then you run it, and you do, it's a computer, very fast, very smart, very thorough, can look ahead many, many moves, and you actually beat the world's greatest human player. That's the old way of computing. It is a model of chess. You can ask, in this type of computing, you can ask the computer, wait, why did you do that? It looks like you just put the queen at risk. Why did you do that, computer? And the computer can tell you. The computer can say, well, human, I figured that even though the queen is worth 50 points, but by putting it at risk and letting it be captured, we're going to be able to move the knight here and the bishop there, and that's going to, etc. It's going to be able to give you an answer that you will be able to understand. Okay, so that's how computers beat the greatest chess master. But a few months ago, Google constructed a computer called AlphaGo that beat the world's third-ranked Go player. And Go, as I'm sure you know, is this enormously complex game. Far more complex, just in terms of the number of possible moves, than chess. Far, far more complex. Much less rule-based. Even the players will say, I don't play Go, but what I've read is the players will talk about intuition. It seems the board is this way or that. Really complex. So AlphaGo beat this player, and it did it without knowing how to play Go. AlphaGo was not given a model of Go the way Deep Blue was given a model of chess. Instead, it was given 130,000 previous games, 60 million moves, and just load up the machine. So this is the part where I'm not being entirely accurate, but accurate enough, I hope. Load up the machine with these moves, let it draw a graph, a connection, using an artificial neural network. So it's a computer that tries to work the way that we, interesting. That tries to work the way we think a brain works, which is a neuron that's connected to many, many other neurons. And each of those, in this case, it's all data. These are little nodes of data. And each of the connections have a computed weight, which says when the node will fire and affect the other neurons. So this works. Obviously it works because, you know, AlphaGo beat the third ranked player. But the thing is that if you, I'm usually excited. So if you ask AlphaGo, why did you make that move? That seems crazy. AlphaGo cannot tell you, or more precisely, it can tell you, but the answer will be, well, okay, human, you want to know? I've got 1 billion neurons, you know, symbolic neurons, so let's start with neuron 1. Neuron 1 is connected to these other 17 neurons. This connection is at a probability of 0.71. This one's a probability of 0.02. Now let's move to node 2. Node 2 is connected to these, and it has a probability, and it goes through the billion or whatever neurons that it has. And you sit there and you're nodding, and you're now 170 years old by the time it's done, and you still don't understand why it made the move. Because it's not following a rule, some higher level abstraction. It's just the computation on all of that data. And well, even if you could take it in and you wanted to see what the next move is, you'd have to feed all of that into a computer to have the computer figure it out. You can't understand why AlphaGo made the decisions that it made, but it's a darn good Go player. It's a better Go player than anybody in this room, unless you are the second-ranked Go player in the world. So here is a computer that does not have a model of the thing that it's helping us to predict. It doesn't know how to play the way that we do. It's a computer without a model, and so are A/B testing. You get results, and you don't know why model on the left worked today. Doesn't matter, you don't need to know. But it doesn't have a model that, sorry, now I'm using model ambiguously. It has the woman on the left. It doesn't have a model that it can give us that we can then reapply and say, oh, models should always be on the left except on Tuesdays, and except for people who've had oatmeal or whatever. So we are getting better at predictions. We're getting amazing at predictions, but far worse at understanding those predictions, why they work. And that actually says something about our idea of how the future works. Because the future does not work the way that we thought it did, the way that we were taught it did, by a clockwork, where we can follow what's going on. We thought that the future arose from causality, and you can trace one ball hitting another, but that's not how it works. It turns out, thanks to what our machines have revealed to us, that everything affects everything, all the time, everywhere, all at once, and will do so forever. Everything affects everything. That's more than our brains can manage. So we are making incredible strides with machine learning, neural networks, with deep learning, in lots of different areas, from advertising to particle physics. It's really, really exciting. This is an inflection point in our history as a species. And not just because we're able to do more, but because it's giving us a different idea about how the future works. That's a very big deal. So the first issue is that there are a whole bunch of ethical issues that arise from this. And these have been getting a fair bit of attention because they're really interesting and they're becoming very pressing. So how many of you have been reading about questions about how to program an autonomous car, a self-driving car, to make decisions about who to swerve and who to drive into? There's some interesting stuff being written. It's a really interesting question. You don't often see applied philosophy. Well, I'll be more specific. You never see applied philosophy. This isn't except now. So the question is, and you can play with this, by the way, a site called moralmachines.mit.edu. So there you will find a questionnaire with a bunch of scenarios. So the first one they give you is, you're in a self-driving car. I keep pointing, even though I know there are people down there who can't see where I'm pointing, but okay. I'm just human. So the first scenario is you're being driven in a self-driving car. It has to make a choice. Should it drive you into a barrier, killing everybody in your car, or should it swerve and hit the pedestrians, including the baby in the baby stroller, and kill them? So you get to vote on this at this site. And I suspect most of you will say, okay, I guess my time to die, rather than hitting the baby. But I don't know, some of you maybe are moral monsters. It's not for me to say. That's up to you, Mercedes has announced, by the way, that its cars will always be programmed to save its passengers, which is monstrous, in my opinion. Okay, so next scenario is you could drive into two sets of people. One is a set of athletic people who are obeying light signals, and the other are a set of, let's say, less athletic people who are disobeying the signals. Which should you do? I don't know, but and so you get these series of choices. This is a nice, fun sort of game, but it's there because somebody's going to have to program these cars to make this sort of choice. And the question is, so right now, if you asked an autonomous car, it could probably tell you why it made the choice that it did. But these cars are going to be networked very soon. And so a network of cars driving down a road can see over the horizon, because there are cars over the horizon who are part of the network. And they will be making decisions that I assume, to optimize a bad situation so that it does the least damage. At least that's what I would want them to do. So these cars already have 360 degrees of data, far beyond what humans can see. We can see 180, if we're lucky, we see 180 degrees, and much of that is peripheral. Multiple cars, long distance, relatively long distance, aware of many, many factors we're not aware of as humans. It may be, if this goes the route of deep learning, of neural networks, which I think would be a reasonable thing to do, that when it steers your car off the bridge, and you don't know why, and you die, and somebody wants to know, it may be like asking AlphaGo. Why'd you do that? I can't tell you. There are many, many factors that you want to know. Let's look at node A. Now let's node 1. Now there may not be a model that humans can understand that is nevertheless a model that does, in fact, optimize a bad situation for the least harm. That's worrisome. It may be a really good thing, because these computers may well be able to make the right decision, where right means, let's say, fewest people killed or injured, or whatever we define right as. But the fact that we can't understand them is worrisome when it comes to life and death decisions, including for autonomous weapons, because those are already here, just as autonomous cars are to some degree here. And they don't look like this guy. They look like the thing behind it, which is much cuter. But it's making decisions about who to kill. And we may well want it to make those decisions. There's reasons why we're building autonomous weapons. So this is a very pressing problem. And if we can't then understand why it decided that it had to sacrifice some civilians in order to achieve it, that's concerning. It's concerning, I want to be clear, it's concerning, but I'm actually pretty excited about the ability of neural networks and deep learning to enable us to understand our world and make predictions far, far better than we could have. I'm not saying that there are issues for sure. So I want to, in fact, suggest that there should be some limits on what we do here. And my example for this is going to be FICO. FICO is a US company that does credit scores, credit risk analysis for customers, and is one of the very big names of it. So it will give you a credit score, and then will tell you what that credit score is based on. Right? So it has a set of factors. So FICO credit scores are based upon a human-made model. They are not deep learning. This is not the neural network thing. This is a set of data scientists who make reasonable decisions about how to assess your credit risk based upon factors that we all understand. So they manually construct a model to do this. And furthermore, so there's a set of things here that determine, that are part of this model, number of inquiries, available credit, so forth. You will not find on this list, however, any percentage given to, for example, your race or ethnicity or your gender or your age or your economic background, economic status, or your sexual preferences. All that's happening. Even if it were to turn out that some of them are, in fact, can contribute to a more accurate prediction. They're out by law. FICO is constrained by US law to only, to first of all, have a manual model, and to make sure that when somebody gets a credit score, or they're denied credit by a bank, and the bank says, look, the credit score is too low, and you get really angry, so, well, why? It has to be explicable to you, to a human being. You can find out why you have this score. You can understand the explanation. It's not some dense formula and calculation. It can be expressed in a human language, and it is based upon factors that you can adjust. If, for example, you were told, I'll just make this up, I'm a Jew, so I'll use Jews, I won't say for that. No, Jews, the percentage of credit default by Jews is larger than the proportion of overall the population, so, and you're a Jew, that's why we turned you down, and substitute whatever ethnicity, gender, et cetera, you want, you would be outraged, and you'd be right to. You say, well, yeah, but that's just discrimination. And that's right, that would be discrimination. That would be nothing, that is what discrimination is. I mean, that is flat out. So they can't use that because they're constrained to only use factors that you as an individual can adjust. So if the bank says, well, it's because you were late past 6 credit card bills that you paid, you can adjust that, you can fix that, you can start paying your credit card bills on time. You can't, if it's because you're black, you can't say, well, okay, I'll change that. You're a woman, yeah, I can fix that. That's not how it works. So there's, I think, very good law constraining FICO to a much simpler model that does not consider some factors that might be relevant. I mean, it's conceivable that age is relevant, but you can't do anything about that. Well, you could wait, I guess, but other than that, there's nothing you can do. So, on the one hand, that's how FICO works, it's credit scores, but when it comes to credit card fraud, no, it uses everything it can, and may not be able to tell you. It may be that you were, if you bought bananas and a bandana in the Bahamas, then you should be, your credit card is at risk of getting Hondas, for reasons that we can't understand, because it's deep learning. So they know how to do this stuff, but they don't when it comes to credit scores. So what does this have to do with ads? The use of models, and I don't mean type I'm showing, computer models and ads. Well, so the first thing I want to say I think is somewhat objectionable, and I'm sorry, but I think that for many advertisers, from my point of view as a customer, what generally we call consumers, but consumers are way too passive. As a customer, it seems to me that advertisers assume in their model of customers that we're always shopping, but we're not always shopping. So we don't always want to see enticements to buy something because I'm not shopping, I'm doing something else. Why do you think I'm shopping? So I think there's an issue with the overall model. My friend Doc Searles talks about this very persuasively. So I wonder what it would be like, and I guess I'm sort of recommending, if advertisers move to a model that was closer to, say, the FICO model, their way of doing models, where if we get an ad, we can find out why, we can understand the explanation as human beings, it's not, deep learning thing, and we get to adjust the factors to say, no, this is not the sort of ad we want. So this would be meaning being more transparent about the factors, using models that make sense to us as humans, and allowing us to fine-tune them. My hope is that this would lead to ads that are more accurate, that we are more willing to listen to, rather than simply getting annoyed about, or blocking. Again, I'll quote Doc Searles, a friend and co-author. He says that ad blocking is the largest boycott in human history. And in some senses, he may be right. So we may be more willing to listen, and it makes the place better. That is, it makes the entire environment a better place to live, which is sort of my definition of being moral or ethical. So easy, and this is where I'll end on this thought. An easy way to think about this is to think about ads more in terms of recommendations. So you're at Amazon, you get a recommendation for something, and you buy something, they always give you more recommendations, because you are now trying, you're at a store, you're trying to buy. And I think people generally like recommendations. They tell you why you are getting those ads, those recommendations, and they let you adjust them and say, well, no, you keep showing me science fiction books, that's because I bought some presents from my niece and I don't really care. Good, take those off, everybody's happier. I know why you gave me those recommendations and I'm able to fix them. There's a very FICO-like approach. So recommendations have some advantages. We pay more attention because we know who's making the recommendation. We already have some kind of relationship. We know why we're getting the recommendation because you tell us. We're not upset that we're getting them because we're shopping. We just bought something or we're looking at something, and we can adjust them. It's just a suggestion, even though suggestions are absolutely ads. Of course they are, when they're coming from a vendor. They feel much better, which means that we will react better to them because they are more accurate, because we have more trust in them. We know we can see why they've been given to us. They well might have more impact, and because they are more human, which is what we are. So it may be, and I want to suggest exploring, that knowing a little less may actually help you to sell a whole lot more. Thank you.